Yeah, so I hope my screen would be visible. Good evening to everyone. So let's start. Yeah, so in last session we discussed a full bridge rectifier, single phase only, with controlled pulse was provided to all the switches, and we discussed resistive load, RL load, and RE load. So RE load basically represents battery charging load. And we discussed a bit about, motor drive load, which was RLE load. So we are going to carry on from that point, and also we derived the output voltage expression. As I told you that if you can see the waveform, you can easily derive the voltage value and expressions. So we will see some problems also based on that. But before let us summarize that for resistive load, since there are no energy storing elements were present in load side, so it will not reveal its energy, and hence it will stop conducting after the duration of pi till the next cycle of switches will be turned on. Okay, so after that, in RL load, we assume that our inductance is sufficiently large so that it will continue the continuous conduction mode, and hence it whatever the energy it stored from alpha to pi duration. I think I should zoom it. So whatever energy this inductance has observed till alpha to pi. And obviously, during this period, some energy would be consumed by resistor, and that would be load, and some energy would be stored by inductor, and the stored energy would be, released during this period from pi to pi plus alpha. Okay, and here we discussed two cases where L is small, then there would be no any voltage, so it will be zero, so no any conduction would be there, and hence we derived the voltage expression for both the cases. When for continuous conduction alpha to pi plus alpha, so it was for like 1/2 time period, and from alpha to pi plus gamma, we assume that pi plus gamma is this period where the conduction is getting stopped, and also for that case we derived the expression, right? Otherwise, you need to remember, so it's better that you plot the waveform. It will just take you, 5 to 10 seconds, and based on that, you just integrate. So it will take another 20 to 30 seconds. So hopefully, within 1 minute, you will be able to solve this kind of problems. Yeah, one question came in last session, that what will happen when alpha is greater than 90? So yeah, it is kind of like important thing. Let me do one. Huh. So based on this concept, uh, some problems has been asked in recent years. So we will see. And also, just to visualize it here, if you put alpha greater than 90, then what will happen? Your cos alpha component would turn out to be negative, right? So if your cos alpha term is negative, means V naught average is negative, right? Because Vm is just amplitude. So if your V naught average is negative, it means, mm, yeah, we cannot reverse the direction of current in load side because it is rectifier. It will always have the flow of current from, plus to minus. Okay. So if it will flow in this manner, and if you are getting V naught negative, right? Earlier it was like that, positive. So, power was V, I was positive. So load was absorbing the power. But when V is going to get negative, your power is minus VI. Okay. And minus VI means now the load will deliver its energy back to the source. What does it means? Some of its energy will be circulated to load, and some of its energy will be dissipated in the load resistance. So basically, that's what we emphasize on regenerative braking, if you might have heard that term. So the basic funda of regenerative braking is to, during braking time, okay, during braking time, our somehow we reverse the polarity of voltage so that that operation will lie in second quadrant, and that will con like reverse the polarity of voltage. And yeah, someone is trying to ask something. Okay, I think he has. Okay. I was saying that if somehow you reverse the polarity of voltage, and that's how you do. Basically, for that purpose, we generally use dual converter kind of thing. So, generally, dual converter will be let me draw the circuit here. So, basically, dual converter is not in gate course, but if you see, so similar kind of circuit Similar kind of circuit would be present here, but in opposite manner, right? So I'm just giving the overview, and this converter will have again some source, and it will deliver for some time period to this load, or it may freewheel its current to the load. So there are several other ways also, or within this circuit you also reverse the polarity of E so that your V get reversed. Or but we were talking about when alpha is greater than 90, then basically you are reversing the polarity of voltage, and you are achieving the desirable thing, which is known as regenerative braking. So that was one thing. So I hope you might have got partially your answer, and we will see this concept with one problem also. So moving ahead,
Hello, sir.
yeah, yeah, please,
Sir,
please.
I am lately joined, sir. So
Okay.
can you say which topic, which concept you?
Actually, I am discussing right now this single phase rectifier. So here we discussed all our RE load, and one question was there: what will happen when alpha means triggering angle of thyristor would be higher than 90? Would it operate or not? So that I was trying to answer. Did you get that question?
Sir, can you repeat, sir?
Okay. So see, the single phase rectifier, right? Controlled rectifier, where
Yes, sir. Yes, sir.
thyristors are getting firing angle at certain angle, right? So uh, many times in some literature, some books also, it is mentioned that alpha should not be greater than 90.
Yes, sir.
It is the case. Do you know that alpha should not be greater than 90 for, a load operation? Means if we are transforming the energy from source to load, then alpha should be less than 90, it is better. Okay, so I am assuming you are new to this concept. So that is the thing I was explaining. So generally the expression of voltage, let us assume for RL load. Here V naught average, we saw that 2 Vm by pi cos alpha. And if you have alpha value greater than 90, then what will happen? This term will be negative, and your average voltage would turn out to be negative. So that's what I was trying to say. And with what are the impacts of negative voltages? That's what I was trying to explain. Did you get the context here?
Yes, sir.
Okay. So we will come back to this again. No need to worry about that. Hmm. So in last session we were still RE load, means battery charging. So the conduction of battery charging was a bit tedious, or I would say a bit complex. How so? See, at alpha, these both switches would be in forward conducting mode, right? At phi instant, this H1 and H2, which is the same circuit of this one, right? This H1 and H2 will come in forward blocking mode, we generally say. Okay. Why blocking mode? Because it will be forward biased, but it will not be able to conduct till we provide the gate triggering, right? So it is mandatory to provide gate triggering to start the conduction of thyristor. So till 5 we can't provide that triggering pulse, okay? Because it will not be in forward blocking mode, it will be in reverse blocking mode till this point, till 5. From 0 to 5, it will be in reverse blocking mode, and hence, even if you provide the gate triggering pulse, it will conduct after 5 only, okay? But after 5 also, till the value of, alpha, means alpha is the value of angle from 0. This is omega t axis. So you may delay the gate triggering pulse, or you can give the triggering pulse at 5 also. Okay. But what happens, the more delay you will do, the lesser period you will get for your active power contribution. So basically, we are getting active power till this period, because that will contribute to your output current, and hence your load will have some active power. And if you started from alpha, but you may anticipate that it will stop conduction at pi minus alpha, because of the same reason. If you start conduction at phi, it will stop at pi minus phi if it were an uncontrolled switch. But now it is not the case. It is controlled switch, so you can start conduction from any point, either here or any point. Doesn't matter. But it will stop conducting when it will come in forward blocking mode or reverse blocking mode. Okay. So at this moment, pi minus phi, this pi minus phi instant, this instant is the point where your E, the back EMF of your whatever this battery, okay, it will be greater than your supply Vm sin omega t. As I took the case of 20 sin omega t, and I took the value of E as a 10. So we derived that your angle would come out to be 30 degrees. So phi was 30 degrees. So your conduction would stop at 150 degrees. So that was the case here. I hope there is no doubt, but still, if there are any doubts, I am ready to take it. You may ask this, because understanding these waveforms and circuits are really important, because wherever you will go, you will find the questions based on these concepts. So, okay, assuming there are no doubts, so uh, after that, if we have the waveform of V naught, we have the waveform of V naught. Now we can easily integrate and get our desirable output voltage average value. So we integrated for pi period, and we saw that the magnitude of V naught is E from 0 to alpha. We wrote the same. After that, from alpha to pi minus phi, it is following Vm sin omega t. We wrote that. After that, again, because we have to go till phi, right? So, sorry, pi. So after pi minus phi to pi, it is again E, right? So we wrote that E again, and after that, just one step, we just integrated that, and we came out with this expression, that 1 by pi E into alpha plus phi plus Vm cos alpha plus cos phi. There is one catch here. where everyone does the same mistake. These alpha and phi you need to take in degree or radian. Can anybody tell me?
Radiant, sir?
Yeah, correct, correct. Radian. We should always take it in radian because it is not angle anymore in terms of degree. If you take degree, it will be too large, right? And if you have some trigonometric function, then you can take degree or radian, doesn't matter. But if you are multiplying with anything, let's say, which is not function of trigonometric or something, so you can take in radian. You should take in radian and you must take it in radian because this is really a common mistake. You should try to avoid. Okay, so we covered RE load. Now we will try to move on RLE load, which is a quite common topic and very frequently questions will be framed on. So let me draw the supply waveform again. Two pi pi. This is Vs and it is following Vm sine omega t. Okay. Now I will draw the circuit again. If you have circuit in front of you, it would be really easy to draw for any kind of load. That's why I am drawing here. Okay. So this is R L E. Okay. Now here RL are also there and E is also present. So that one condition that we need to satisfy first. What was that condition? Vm sine omega t must be greater than E to conduct or to supply the power to load, right?
E, sir.
Yeah, E. I wrote this E, right? Any issue there? Hmm. Now, this condition must satisfy. It means omega t, if omega t is greater than sine inverse E by Vm, then only these both thyristor H1 and H2 will start conducting. Okay. So let us take again this omega t was 5. Now we will draw this on waveform. We will take one step at a time, right? So that it will really fit in our, yeah, so this is 5. Okay, so we are going to start from 5. Okay, now before 5, what would be the, your magnitude? It will be E, right? Because if you see voltage at this node, let's see, these both are the nodes here. If you see V naught, if no current are flowing, okay, let's suppose I naught is 0, and that is obviously when no switches are conducting, so you are not getting any supply from source side. So V naught is E. Directly KVL you can apply, right? V naught is equal to E. So it will be E till 5. After 5, this both H1 and H2 will come in forward blocking mode. It will come in forward conducting mode whenever you will provide the gate triggering pulse. Let us suppose you provided gate triggering pulse again at alpha, and this alpha is duration from this 0 point. It will again follow the same. Okay, so this is again alpha, and it will follow the supply voltage till at least pi minus alpha, right? So let us suppose this is pi minus alpha. Okay, it has followed till pi minus alpha. Now the inductor, this inductor value get charged, right? Because inductor has to dissipate its energy, whatever it has stored during the period of storing the energy, right? Because till this point it was storing the energy whenever this I naught was flowing. So the stored energy half Li square now will come in picture, and this energy of Li square depend on two things, right? L and I. Okay, I is fixed. You cannot change I. But L, you can design of higher inductance or lower inductance. So if your inductances are sufficiently high, then it will start conducting. Let us assume your inductance is very high. Generally, in gate problems, it will be mentioned that your inductance is very high. Assume and I naught is constant, ripple free. So it means that it will now follow the supply voltage waveform till what instant? Could anyone let me know, please? If your inductance is really very high, okay, so it will follow your supply till which instant? Phi, alpha, pi, whatever. Any guess?
Pi plus phi.
Pi plus phi, that is correct. Till pi plus phi, it will definitely conduct. But still, your this H3 and H4, they will come in forward conduction mode after pi plus alpha, right? So if you are saying that your conduction will go on till pi plus phi, then you are you mean that it will not conduct for this period from pi plus phi to pi plus alpha again, and it means it will again follow this kind of waveform, and it will again follow the pattern of supply. But your inductance was very high in the first place, so it will not let your converter go in discontinuous conduction mode. Okay, so what I mean by that, it will conduct till pi plus alpha, because inductance means you have no lack of energy. You can supply till whatever point your devices can conduct. Did you got that point, no, Kirti?
Yes, sir. Now I got it.
Yeah, so that's why I emphasized on each and every step. Sorry. Yeah. So it will conduct till pi plus alpha, and again, when at alpha, your H3 and H4 now come in forward conduction mode, it will follow V naught is equal to minus Vm sin omega t, right? So it will go up and it will conduct, and it will be periodic after each period of pi, right? So this kind of waveform you may have seen. Huh. Now the question is why I drew this E, right? Now I can easily eliminate. I just wanted to, confuse you guys that you will say that it will be E after, pi plus phi or something. But it will be periodic after every pi plus alpha. Okay? So its waveform would be like this. Okay, this was the first case when inductor was very high. And generally this is the case which is asked in gate, but there is no certainty that you will be asked the same kind of problem. Now, okay. So for this kind of waveform, we will find out the output voltage. Again, since we have the waveform, we will do it quick. We will take pi period from alpha to pi plus alpha. We will integrate Vm sine omega t. We do not have to bother about E or anything else because they are not coming in picture. Or we do not have to bother about any discontinuity because our inductance was really high. Okay. So you will get again the same value 2 Vm by pi cos alpha. Okay. Now, okay, one more thing I wanted to explain right here. From this waveform, you can see your alpha is just near the pi by 2 period. Okay. If you increase this alpha, if you increase this alpha, you will see the pattern like this. And let me draw this also. Okay. So let's suppose your alpha is 120 degree. Okay. So it will start from 120 to pi by 3 and it will follow the supply till pi only. Okay. After pi, it will follow your negative pulse, right? Because your supply has negative thing and H3 and H4 yet not come in picture. Right? Now at pi plus alpha means pi plus 2 pi by 3, your H3 and H4 will be triggered and again it will follow the pattern. So now from this waveform you can see that your negative portion is higher than your positive portion, right? So obviously from waveform also you can see V naught is negative, right? So it means your power will be also active power delivered from the load side. Okay. Now the second case that I will consider for discontinuous conduction mode of this thyristor when L is not sufficiently large. Okay. Okay, so we will start from alpha. Okay, because let's assume this is phi, and when we go on, this is pi. It will start immediately at alpha. It will catch the supply voltage waveform, and it will follow. No, this is not the shape of supply. Will follow the supply. Let us assume till pi. After that, again for certain period, because for this period, your inductor will consume some energy or store some energy. It will dissipate, and since your inductance value is less, it will stop conducting at again pi plus gamma. Now, at pi plus alpha is a bit higher value than pi plus gamma, so it will not conduct for this period. Okay, from pi plus gamma to pi plus alpha, conduction will not take place and it will be in discontinuous conduction mode. And again, at alpha, it will catch up and it will follow the same kind of waveform. Okay. Is there any mistake in this waveform?
So E value.
Yeah, perfect. So we did not took E in account. Okay, so it is kind of waveform of RL load. It is not for RLE load. If you take E in account, this level will be shifted up to E. Right? E. So this will be the kind of waveform that you will see. Someone wants to ask something? Okay. So this is kind of your waveform. Now it is wise to move ahead with alpha
It is
angle.
positive, sir.
Yeah, it is positive here because if you see where is the circuit? Yeah. So whenever either of thyristors are off, let's suppose all the thyristors are off, that is the case from pi plus gamma to pi plus alpha, right? Then what will you see here as V naught? You will see only E, right? And E polarity is like this, so V naught is equal to E. Am I right?
Yes, sir.
Yeah. Now again, we will integrate it and we will get the value. Again, we will take pi. Now we will integrate from alpha to pi plus gamma. Sorry for that. I think my internet connection is a bit poor. Yeah. So from alpha to pi plus gamma, it is following the supply. So Vm sine omega t. From pi plus gamma to, okay, let me open this one more, I guess. Hope I can copy this in. From pi plus gamma to pi plus alpha, it will be E into d omega t. Okay. Now we can easily integrate it 1 by pi d omega t Vm cos alpha minus cos pi plus gamma. Okay, that will lead to minus cos gamma. Okay, cos pi plus theta is minus cos theta plus E into pi plus alpha minus pi plus gamma, it should be minus pi plus gamma. So this is your average voltage expression. Okay. Now you can just simplify it 1 by pi Vm Vm cos alpha plus cos gamma plus E into alpha minus gamma. So this will be your overall expression, what you will derive after looking at the waveform. Okay. You just need to be concerned about drawing the waveform. After that, everything will fall in place. So any doubt in this topic? Almost single phase controlled rectifier is finished. We will see some problems, and after that, we will be good to go. Ah,
Clear, sir.
okay, thanks. Yeah, any doubt? Okay, so okay, I think one thing I wanted to discuss. Okay, I have muted him. So we need to find all the distortion factor things, distortion factor, THD, and this fundamental component, RMS components, so that we can do. Although I have done the same thing with switching function thing, but since we have switched to this conventional thing, so just I will derive it in 5 minutes, and after that we will do that. So let us suppose, let me bring back the circuit. Yes. Just a second. You just need to find the relationship between source current and load current. Okay. So from this figure, you can see when H1 and H2 will conduct, Is is equal to I naught. And when H3 and H4 will conduct, your Is will be equal to minus I naught. Okay. So for controlled one, the conduction started from alpha and it went till pi plus alpha. So for this period, your Is would be equal to I naught. Okay. And from pi plus alpha to 2 pi plus alpha, your H3 and H4 will conduct and it will be minus I naught. Now we have the waveform. We know the standard Fourier series of this kind of waveform from 0 to pi and pi to 2 pi. Even you could derive this also, but since you are dealing in power electronics, at least you should know the Fourier series of this kind of a square waveform. It's just 4 I naught by n pi, nothing else. So if you write Is of this kind of waveform, let me tell you, second. So second kind of waveform, you will get summation of n is equal to 1 to infinity 4 I naught by n pi sine in omega t. Okay. Since you know the Fourier series of this one, if you have difficulty in believing this expression, I have derived this kind of with switching functions also, or you can derive with conventional A and B and type of Fourier series approach also. Okay. So this waveform is nothing but the shifting version of this one, right? IS1, let us assume this is IS2. So IS1 is a right shifted of IS2 or delayed version of IS2. So if it is delayed means we are going to subtract the angle from this omega t. So let me take the first waveform. Is will be same, magnitude will not change since magnitudes are the same, just it is getting shifted. So you will just do the shifting in angle. So sine in omega t, the angle was alpha, right? So that's it. This is the Fourier series of Is. Now, to compute the distortion factor, which is represented as Z, Z is nothing but Is1 fundamental RMS divided by total RMS. Okay. So that you can see how much the percentage of fundamental is present in this kind of a square waveform. Okay. Because the only useful components are fundamental really. Because why? You are providing fundamental kind of or sinusoidal, which is only have a single frequency component, Vm sine omega t. There are no terms of 2 omega t, 3 omega t there. Okay, if you would have some kind of that, then that would get accumulated with those components of your current, and then it will lead to your active power. But now it won't. So now you want to know what are your useful content of this waveform. So for that purpose only we do this distortion factor calculations and total harmonic distortion, how much it is. So IS1 we can easily compute from this one. You just need to put the n value of 1 in this expression, and you are just concerned with magnitudes here because angles are just the for reference from where you are starting. Okay, so the magnitude of this IS1 was 4 I naught by pi, and since we are taking magnitude of fundamental and it is sinusoidal, so RMS of it is divided by root 2. You have 2 root 2 by pi I naught. Okay. Now what about IS RMS? So if you talk about IS RMS, and let me write it again. IS RMS is 1 by 2 pi. Is from 0 to pi. Is magnitude is I naught square d omega t, plus from pi to 2 pi. Is is minus I naught square to d omega t. Okay. If you compute it, you will get I naught. And you could also, just by seeing it, you could write it. If you square this waveform, it will have I naught square throughout the time period. Okay. So if you have I naught square and if you are doing root mean, so you just you just need to take the under root of that, you will get I naught. So from just by seeing those waveforms also, you can write ISRMS is I naught. Okay. Now here, IS1 RMS we computed 2 root 2 by pi I naught. Okay. And ISRMS is I naught. I naught will be cancelled. You have the distortion factor of 2 root 2 by pi. Okay. If that you will compute 2 root 2 by pi, let me compute it. So this value will be 0.9. It means this kind of Fourier series or this kind of current, what you are achieving at load side, and that is basically coming from your source side. So your source component has 90% of, useful component of current. You can say in layman terms, whatever the useful component of your source current, that is only 90%, right? So how much distortion are present, right? Ideally, your waveform should be, IS should be this one, okay? But now your IS will not like ideal thing. It will be mm, kind of distorted, okay? And this kind of distortion we generally limit with hysteresis controller. So we limit those kind of band. So after those bands, it will not affect. So that is one approach. So now I will found PhD that will be 1 by G square minus 1, and you can put it here 1 by zero point 0.9 square minus 1, and if you compute it 1 by zero point 0.9 square minus 1, so you will get 48.43 percentage, okay, percentage THD if we are talking, and that is huge, okay. Mm, your THD is very high, but you can't do much. Otherwise, you have to shift with higher number of phases. So that's why three phase will come in picture. Similar situation I explained with switching function things also in the starting, that what are the drawbacks of this kind of converters. So you may look again at those lectures. Okay, so we are done with distortion factor, switching function, sorry, not switching function, this distortion factor and all kind of voltage average. And yes, if you need to compute I naught at any point of time, you just need to look at the load side. So let us suppose if your load has R and E kind of thing, you computed V naught from your voltage waveform. Okay. You just need to apply your KVL V naught is equal to I naught R plus E. You can do L di by dt, but in one time period or in average sense, it will fall back to zero. So you may ignore it, and you should ignore it basically in common sense. So your V naught will be I naught R plus E. Okay, any doubt?
Clear, sir.
Okay, thanks. Some comment I can see. For our discontinuous current mode, what is the peak value of instantaneous current? Okay, interesting question. What is the peak value of instantaneous current? Okay, instantaneous current. Yeah, see, source current is depending on your load current, right? And the peak value, this expression of Fourier series is nothing but your instantaneous value, right? At any point of time, mm, basically fundamental component will be higher, right? If you take n is equal to 1, you will have 4 I naught by pi, right? So your 4 I naught by pi is only peak current. Whether it is discontinuous or continuous, 4 I naught by pi is your peak component. So you should not bother about other things. So it is 4 I naught by pi only. Are you convinced, Prem? Okay. I will take that as yes, I guess. As I'm in library. Okay, you could comment here. It doesn't matter whether it is discontinuous or continuous. If it is discontinuous, your average V naught will get reduced, and consequently your I naught will get reduced. So whatever I naught will change, whether it is discontinuous or continuous, since V naught will change, and appropriately your I naught will be adjusted. So I hope I am able to convince this point. Okay, great, thanks. So now we will take one or two problem. Okay. And in next session, I may go ahead with half
Varam.
control. Yeah, someone is trying to say something.
यार वाला
Sorry, I couldn't get it. Could you repeat it or could you write in chat box?
हाँ यार
Okay.
हाँ हाँ same
Yeah,
हाँ
yeah.
same
Okay, I think you are mistakenly unmuted. I will
हाँ
have to mute you. Okay. Hmm.
hello sir.
Yes, go ahead,
Yeah,
please.
which book you taken, sir? Net book, Net Mohan or M. What, sir?
Ned Mohan is fine. Otherwise, if you want to go deep in rectifier, Ned Mohan is basically sufficient book for like DC-DC converter and rectifiers. It is a sufficient book. Ned Mohan and
Daniel Mohan, sir.
Daniel Hart is good for DC-DC converter. I haven't referred it for AC to DC converter. I will see once and I will let you know in next session whether it is good book or not. Otherwise, you can blindly follow the Ned Mohan. No issue.
Okay,
Daniel Hart is really good for DC converter. I have referred for that, but I forgot because generally we refer three, four books.
from which book, sir?
You, Ericsson is also good for AC to DC rectifier. If you search that, I have that book maybe. Have you heard about that book, Ericsson?
Sir?
Have you heard about that book by Ericsson for power electronics?
No, sir.
Okay, let me write the name of that book. Okay,
Okay.
I will write the. Oh, the book name is Fundamental of Power Electronics by Robert W. Erickson. I'm typing it in chat box. Yeah, so that's the name of the book which I just wrote. And I hope one problem you might be able to see on the screen.
Yes, sir.
Yeah, so that was asked in 2010. So in problem, it is saying that a three-phase fully controlled converter is feeding a load whose current is constant, means load current is 10 ampere and firing angle of 30 degree. So alpha is 30 degree. Oh, sorry, I took the question from three-phase. Yeah, so this is based on single phase. So they are asking about input power factor. Okay. Again, alpha is 30 degrees same. And now the load current information is not there. Okay. So how would you proceed? So we know input power factor cos phi is or it has relation with cos alpha into distortion factor, right? Now, for single phase fully bridged converter, G is your IS1 by IS1 RMS by IS RMS, and we just now computed IS1 RMS by 2 root 2 by pi into I naught, and IS RMS was I naught. Since it is also mentioned that load is drawing constant and ripple free load current, just what I told you, that generally it will be given that your load will draw constant and ripple free load current. So you can assume it for continuous conduction, right? And the type of load is also not mentioned. So if the type of load is not mentioned, you can follow the continuous conduction kind of thing. Okay, this kind of voltage waveform will be there. And so V naught also you can directly write 1 by pi from alpha to pi plus alpha Vm sine omega t d omega t. See, I just drew the waveform and I can write its expression just by looking at the waveform. So that should not be the issue, and you will get 2 Vm by pi cos alpha. However, this information is not required in this problem. I just wanted to show that anytime you could compute. Now, cos alpha, alpha is 30 degree. So cos phi is equal to cos 30 degree into 2 root 2 by pi. So if you compute this value, 0.9 into cos 30, so that will be 0.778. So your input power factor will be 0.78, you can say. Yeah. So which is really less, but you have to manage with this kind of converter. And that is the reason you should not provide the highest delay angle or triggering angle. You should maintain it, near to zero crossing point so that your cos alpha would be minimum. And when your cos alpha would be minimum, G anyway is fixed for any given converter or for any given conduction mode. Cos alpha you can reduce and cos alpha you can improve to for the improvement of power factor. Right? Any doubt in this problem? Okay. Just one quick question based on battery charging. Okay. Yeah, this problem was asked in 2008. Okay. So this is half wave uncontrolled AC DC converter. Okay. Now here they have introduced the concept of a step down transformer. Since we have 230 volt 50 hertz of supply at our home, so it will be connected with this 230 volt 50 hertz. Okay, and this transformer is feeding this half wave uncontrolled rectifier. Okay. Uncontrolled means diode. You can represent it with diode. And this is our E load. Okay, and its turns ratio would be 4:1. Okay, so we just need to find out the voltage at this node. Okay, if we compute this node voltage, our work with this transformer is done. And
Excuse me, sir.
yeah,
Sir, is your screen stuck at previous question or any problem with my network?
I think it should be visible with other users. Others can confirm it. Anyone, is it visible, this problem with
No,
transformer?
sir. For me also, it's like partially it's come, sir.
Okay, okay, so let me just reshare it. Okay, and now I think it should be visible. Is it?
Yes, sir.
Yes, sir.
Okay, thanks for letting me know. Uh, so yeah, so again, please see at the problem. This was the problem. Single phase 230 volt 50 hertz AC mains was fed through a step down transformer through a half wave uncontrolled AC DC converter with charging a battery of 12 volt DC. So since it is written that it is charging a battery, so it means we can infer that it is RE load, right? Now it has series current limiting resistor of 19.04 ohm, okay, and E is 12 volt, right? So now it is asked that charging current. So you have to infer from this circuit your charging current would be I naught, okay? And if the first task is to compute your V2, V2 will be computed with the help of turns ratio. V2 by V1 is equal to N2 by N1. Okay. So now if you plug in all the values, so N2 by N1 is 1 by 4 into 230. Okay. And this 230 is RMS value of sinusoidal component. Okay. So that will be 115 230 by 4. That is 57.5 volt. Okay. So this is your V2. You got V2 and V2 magnitude would be 57.5 into root 2 into sine omega t. Okay, this would be in terms of amplitude. Okay, now to compute V naught, V naught I mean at this node, okay, V naught, it will have the same expression. Just let me draw the waveform just in a second. Till phi, it will be E. From phi to pi minus phi, pi minus phi, it will be Vm sin omega t. Again, from pi minus phi to till 2 pi, it will be E. Okay. And since it is a half wave converter, you have to consider entire 2 pi period, right? So we will integrate it for 2 pi period from 0 to phi E into d omega t, from phi, phi to pi minus phi Vm sin omega t plus pi minus phi to 2 pi. It is again E into d omega t, right? Now you just need to plug in all those values, right? E was 12, I guess. Yeah, 12. Vm is 57.5 into root 2, and again E V naught 12. You just need to integrate it. You will get a value of V naught, okay? And after V naught, you just need to compute I naught, which will be computed from this KVL equation. V naught is equal to I naught R plus E. You know now V naught, you know now E, you know you have R. That is current limiting resistor. Okay. So all you need to find out is the remaining I naught, and that you can easily compute. Okay. So I think you will be able to compute this, right? Or otherwise, I will complete it in next session since time has been come up. Hello, is it fine? Can anybody let me know?
Yes, sir. We will compute it.
Okay, thanks. Thanks. So, any doubt regarding today's session? Any
No, sir.
fine?
No, sir.
Okay, thanks. So, in next session, we will discuss single phase controlled half wave controlled rectifier with three phase rectifier. Okay, thank you. Thank you, Anu. Thank you, Prem. Thank you, Nokirti. Thanks, everyone. So,